Hey everyone, welcome. So today we're going to dive into a really classic coding problem, finding the longest subarray of numbers that adds up to a specific value, k. But here's the thing, this is way more than just solving one puzzle. We're about to unlock a core pattern that's going to totally change how you look at a whole bunch of other coding challenges. I mean, really think about that for a second. Instead of trying to cram dozens of different solutions into your head, what if you could just master one powerful technique that cracks them all? Well, that's exactly what we're going to do today. This is all about working smarter, not harder. Okay, so why are we focusing so much on this one problem? Because honestly, it's like a master key. The return on your investment for really, truly getting this pattern is huge. Once it clicks for you, I promise, you're going to start seeing it pop up everywhere. And when I say everywhere, I'm not kidding. This idea isn't just for number arrays. You can use the exact same logic for problems with strings, for balancing binary arrays, finding stretches with equal ones and zeros. And yeah, it's a total staple in technical interviews. Mastering this is like adding a brand new Swiss Army knife to your toolkit. All right, before we get to the really cool, elegant stuff, you always got to start simple, right? Let's talk about the brute force way. If you had no tricks up your sleeve, how would you tackle this with just pure, straightforward logic? The logic is pretty simple, You'd basically have to look at every single possible subarray. For each one, you add up all the numbers inside it. If the sum happens to equal k, you check its length. If it's the longest you've seen so far, you make a note of it. Yeah, it'll get you the right answer, eventually, but there is a huge catch. And that big catch, it's all about speed, or the lack of it. This method has a time complexity of O of n squared. That just means that as your array gets bigger, the time it takes to solve explodes. It's just way too slow for a real interview or any practical application. We need something much, much faster. Okay, so that slow way is out, which brings us to the aha moment of this whole thing, the prefix sum trick. This is the secret weapon, the core insight that lets us just blow this problem wide open and solve it in a super efficient way. So what in the world is a prefix sum? Well, it's actually just what it sounds like. It's the running total. As you walk through an array, it's the sum of everything from the very beginning up to the point where you are right now. So if you have an array like 1, 2, 3, the prefix sums are, well, first it's 1, then 1 plus 2 is 3, and then 3 plus 3 is 6. Simple, right? But oh, it is so powerful. And here is where the magic happens. Once you have all those running totals, you can find the sum of any subarray you want instantly. The sum is just the prefix sum at the end of your subarray minus the prefix sum from right before it started. Boom! No more nested loops, it's instant. Okay, stick with me here. This is the really clever part. We can now reframe our whole problem. We want to find a place where prefix end minus prefix start equals k. With a tiny bit of algebra, we can flip that around. It becomes prefix start equals prefix end minus k. So our new mission is this. As we're walking along calculating our current prefix sum, we just have to ask, have I seen a previous sum that's equal to my current sum minus k? You know that question we just asked, hey, have I seen this number before? That should set off alarm bells in any coder's head. To answer that question instantly, we need to add a supercharger to our algorithm. And that supercharger, my friends, is the hash map. I mean, this is literally what hash maps, or dictionaries in Python, were born to do. They give us what's called constant time, or O of 1 lookups. As we calculate each new running total, we can store it in the hash map. That way, we can check in an instant if the exact value we're looking for already exists. And this is the payoff. This is why we do all this. We're going from a slow O of n squared solution to a lightning-fast O of n solution. We just have to walk through the array one single time. We're not just making it a little faster, we're going from crawling to light speed. And that's the kind of leap that makes all the difference. Okay, one really, really important detail here. Don't miss this. What if we see the same running total, the same prefix sum, more than once? The rule is you only store it in your map the very first time you see it. Why? Well, we're looking for the longest subarray, right? An earlier starting point will always give you a longer result. So we lock in that very first index we find to give ourselves the best possible shot at a record-breaking length. Okay, enough theory. My brain's starting to melt. Let's make this real. We're going to walk through an example step by step. Let's use the array 1, 2, 3. And we're going to be looking for the longest subarray that adds up to our k value, which is 3. All right, let's set the scene. Our max length starts at 0, obviously. Our running prefix sum also starts at 0. And then we do this clever little setup. We put an entry in our map, 0, -1. Now, this might look weird, but it's a pro move that cleverly handles cases where the subarray we find starts at the very beginning of the array. You'll see exactly how it pays off in a second. Okay, first up, the number 1. Our running total, our prefix sum, is now 1. So what are we looking for? We're looking for prefix sum minus k, which is 1 minus 3, which is -2. Is -2 in our map? Nope. Okay, no match. So we just log what we did see. We saw a sum of 1 for the first time at index 0. Let's put that in the map and move. Next up is the number 2. Our running total was 1, we add 2, so our new sum is 3. Now, we ask the question again. What are we looking for? We're looking for 3 minus k, which is 3 minus 3, so we're looking for 0. Let's check the map. Do we have a 0? Yes, we do. This is where that 0 minus 1 setup comes in clutch. We found our target. So the length is our current index, which is 1, minus the index we found, which is -1. 1 minus -1 gives us 2. Our new max length is 2. On to our last number, 3. The running total was 3. We add 3, so now it's 6. What are we looking for? 6 minus k, so 6 minus 3. We're looking for 3. Is 3 in our map? Let's check. Yep, it is. We saw it back at index 1. So the length of this subarray would be our current index, 2, minus that found index, 1, which is just 1. Is 1 better than our current max length of 2? Nah, so we don't change anything. And that's it. We're at the end of the array. The final answer we have is 2. The longest subarray with a sum of 3 was 1, 2. Our algorithm worked perfectly.
And just like that, you've unlocked the pattern. This is your new superpower. But of course, a superpower is only useful if you know when to actually use it, right?
So here's the mental checklist. The next time you see a problem, if it talks about subarrays, if it involves sums, if it asks you to find the longest something or the count of something, and this is a big one, if it allows for negative numbers, your brain should just light up and scream prefix sum plus hash map. And let's bring this full circle. Remember how we started? This one idea solves so many other famous problems. Finding a subarray that sums to 0, that's just our problem with k equals 0. Finding a subarray with an equal number of zeros and ones, just pretend the zeros are negative ones and look for a subarray that sums to, you guessed it, 0. It's the same engine under the hood, just with a different paint job. So there you have it, a powerful, super efficient pattern that you can use all over the place. You've got the tool in your belt now. The only question left is, what problem are you going to solve with it first?